Boom. Hello and welcome back to Calculus 2. We are going to apply all of this awesome math knowledge and talk about physics. So, the order in the world is mathematicians are first to figure something out, then physics finds what that models in the world, and then engineers figure out how to put it to the good use, then the workers make it, and then finally we can spend money on it and buy it and use it, right? So we are going to show a few of the concepts in physics done where we can use integrals. You've seen in Calc 1 a lot about velocity, acceleration, position, and all of these cool things. Now we're going to talk about mass, which is we are going to quantify. We're going to quantify that aspect of our reality. So the definition of mass is going to be the integral of density function. So I like to define mass. This is me. Like to define mass as the quantification of physical existence. So, you know, there is energy, which is actually also a form of mass. E equals mc squared, so energy and mass are interchangeable, actually. They're the same concept. We don't see it that way, but they are, and one creates the other. If you pump enough energy in a small region of space, you are going to create particle and antiparticle, and then if they collide, they will annihilate each other, cancel each other out back into energy. So the matter and antimatter pairs. So mass, I like to think of mass as the quantification of physical existence, and the mass is going to be defined with the m, right? It's going to be defined as the integral of density function. So a to b rho of x dx. Now this is a Greek letter rho, which is equivalent to our lowercase r. So we see here this is an integral. We know that integrals add and accumulate. Therefore, the more dense objects should have more mass. So this is the mass in one dimension. You are going to have integrals for mass in 2 dimensions and 3 dimensions and so on as soon as you take Calc 3 class, which is next, right? In Calculus 3 you are going to see the integrals. I think I actually have them here on the, there it is. So this is the integral that we just covered, and you mention it again in Calc 3, and then you do one example, and then here is the 2D. So this is the integral that I'm talking about for 2D, and then there is one for 3D. So all of these integrals, later on you will have integrals to figure out the mass for other objects as well. So this is the 1D mass. Now what this is the long rod, right, which doesn't have to have uniform density. Objects are usually not of uniform density. Like if you think about this marker, which is long, there is a different density in this area here, and this area here, and the area at the end. So we can think of constant density. So if we have a constant density or uniform, it's going to be rho of x equals some value, call it k, value k. All right, so it's constant density. So in that case, the mass of the object would be just integral a to b of k dx, which is kx of AB, and you get KB minus KA, which is a number, right? All of these become constants. A and B would be the length, the distance between the two objects. So this is the one-dimensional mass, and we are talking about a long rod from A to B, which has the density function rho of x, which will give us the mass. Now, we can have the non-uniform, right, the varying density, and then you will have to integrate. So I'm just going to pull one problem from homework for that. Problem 16 looks great. So the density function rho of x is given as a piecewise function because the density is really crazy. Like marker would be something like that. These abrupt changes. X and then x2 minus x. And then we have, this is from 0 to 1. And this is from 1 to 2. So to find mass, I have to do two separate integrals, and I have to add them up. This would be equivalent of, let's say, this represents the cap of the marker, and this is the body of the marker, let's say. So to find the mass, I will have integral from 0 to 1 of x squared dx, plus another integral from 1 to 2 of this 2x minus x squared dx. So I'm simply integrating the function on its domain, but each one has to have its own integral because they are different functions. And then I add those two masses together to get the mass of the entire object. So we have x cubed over 3 from 0 to 1 plus x squared minus x cubed over 3 from 1 to 2. This is going to be 1/3, and then zeros don't contribute in this case. And then we have plus 4 minus 8/3 minus 1, and then plus 1/3. So 1/3, 1/3, that's 6/3, that's -2, 4 minus 2 is 2 minus 1. So I think all of this is 1. So 6/3 is 2, 4 minus 2 is 2, minus 1 is 1. Good. 1. They did not give us units, so I'm not sure what units these are. Grams, kilograms. What is the unit for mass in imperial system over here? No, that's the units of force. Kilogram is the SI, the System International. That's in Europe. What's in US? Newtons are force in SI system. That's force. Pounds is force. He's looking it up over there. It's a slug. Slug. Yeah? I know. See, when you go in Europe and you buy 1 kilogram of bananas, you actually paid for bananas. When you buy 1 pound of bananas here, you pay for the force that pushed the bananas. You paid for the force that pushed into the scale. Anyway, you can cheat the system, because if you are buying it on the top of Mount Everest when the moon is directly above you, you pay less. Because you are paying for the force, it pushes it up, right?
Climb Mount Everest, find your local banana shop, and stock up.
And build a
Yeah.
banana shop and then
wait till the moon is right
at the
above you.
moon.
Yeah. The hypothermia. Bring the blanket. All right, so now we understand mass to some point. You will remember the slug, I hope. and research that. I believe slug is about 15.1 kilograms or something like that. So it's.
Should we multiply it to the 1 as well? Get the hard, get the slug unit and all.
No, this is just me asking you to look up the units. All right. So now we are going to talk about the force and work.
Work on the force.
Yep.
The work with the force isn't like the same and all.
Well, work is equal to what? Work is equal to force times the distance, right? That's the major constant. But the trick with this is that if you are using constant force and you're covering certain distance, right? You're calculating this linear type of a work. But what happens if it's a varying force? You see? If you just use this very basic formula in physics, it doesn't really paint the reality. Because if you, let's say you need to push a fridge, right? You don't start pushing the fridge with the force that you will actually be pushing the fridge at all times. The first contact, and you're still not pushing it, but you are touching it, so that's where the force is 0. And then you are starting, right? The same like driving. You don't, well, except probably him, but everyone else, you don't start 60 miles per hour, right? You don't jump into the car that is already 60 miles per hour and just drive 60 miles all the way to your destination and you jump out. There are also, right, there are red lights and suggested stop signs and all that kind of stuff. I have to look at him every time I say that because he disclosed the information. What can I do? So, so the same thing for the force, right? When you make the contact with the object, you are still pushing it with 0 force, and then you start pushing it, so the force rises. So the graph of that would be, you start when you touch, and then the force, this is the force in time. So it starts with 0 when you touch, and then you push, and now you're pushing, and then you guess what? You're getting tired, right? So there is a function. There is a function that describes this, so you will call that f of x, which is the force function. So now it's not uniform. It's not 60 newtons across the board. It starts at 0, it rises, it falls as you get tired. You know, you get distracted for a second, right? Everyone else is pushing, you're not. And all of that stuff. So now, when I'm talking about this, I know that the force I'm going to replace with f of x, and the distance is going to be our dx from A to B. So there is the work when you have the variable force. So in your basic physics course, you just learn W equals F times D, but that's when the force is uniform. Calculus allows you to have varying force. So this is a big equation. And we usually describe the work by simply pushing an object, or most of the time considering springs as one of the very important mechanical devices, right? Because springs store the energy and release and so on. So it is overkill to use this integral on the basic physics problems. You can, but it's overkill. If you have a crate, which you are pushing with 60 newtons of force, let's say 3 meters, then you can just say 60 times 3 is equal to 180, or you can go 0 to 3 of 60 dx, and you will get 60x from 0 to 3, which is 180. Newton meters. That's the units, Newton meters for work. So it's overkill to use integral on basic problem which you can only solve as force times distance. But when the force is variable force, well, then you have to use the integral. So let's take a look at springs. We look at the Hooke's law first, and Hooke's law says that the force is equal to kx. It should be negative kx, but in math we just put kx. Negative because of the fact that whatever you are doing to the spring wants to do the opposite. So it's the ultimate rebel, all right? If you compress the spring is pushing outward. If you stretch the spring is pushing inward. And when you leave the spring alone, it's in equilibrium, but then you're not doing anything, right? So that's Hooke's law. That the force is kx. Now this k over here is the spring constant. And the spring constant is describing the type of the spring you have. You know that you have the spring in your pen that you click, right? Which is the spring is the one that pushes the button out. So you have the spring in your pen, but you also have a spring in a suspension of a truck or a train. And that's a little bit different spring, right? Actually, it's not. They both have the same shape and the same purpose, but the one that is on the train supporting tons and tons of weight, that spring has much bigger spring constant. So you can look at the spring and say, okay, these numbers are for pens, these values are for cars and for trains and so on. So spring constant is actually telling you how stiff, how difficult it is to compress spring, how much force you need to apply to compress the spring. And x is clearly the distance that is given. So now, when you are considering work, you know that work is the integral of the force. You can see that the work done by the spring is the amount of either stretch or the shrink of the spring, k times x dx, where k is the spring constant. So say you have an object that you want to push with the spring. And let me just pick the numbers. So it's supposed that a force of 10 newtons stretches the spring 0.1 meters. So 10 newtons can stretch the spring 0.1 meters.
Wait, what does that first word say?
Stretch. That's a T and then C and H.
No, I meant that after ION or...
That's 10 newtons.
Oh.
It's not ION, it's 10 newtons. 10 newtons can stretch the spring 0.1 meters. So 10 newtons can stretch the spring 0.1 meters, which means K is 100 newtons per meter. Those are the units for this. All right, so now how much work is done by this spring to compress 0.5 meters from the equilibrium position? So you want to stretch 0.5 meters from equilibrium. Guys, equilibrium equals 0. If I am compressing the spring, that means that I'm going in a negative direction, right? So the integral has to be from 0 to negative, what was that, 0.5 meters? 0.5, half a meter of our 100x dx. Remember that in the formula we had k times x, right? And we just found k is 100. The integral of this is 50x squared from 0 to negative 0.5. So 12.5, right? Newton meters.
Where did you get the negative 0.5 from?
I want to compress the spring half a meter. Compress the spring. Yes.
What if I want to stretch it 0.5 meters?
That's next problem.
If it's always times x, then wouldn't the integral always have the squared, so the negative wouldn't
Yes,
matter?
because it doesn't. It's the same spring. You can't change the spring constant, right? So it's just for the reference frame in which direction you're going. But whether you stretch the spring or compress the spring, it's the same amount of energy. It just depends on which way it goes, right? Now, Kevin, you wanted to stretch the spring 0.5. So that would be the same problem, except now it's 0 to 0.5. It's a positive, but it's the same value at the end because it was squared.
It'll be the same thing, though.
Yes.
Well, no, just trolled you.
Yep. Come on.
Yeah. The ultimate troll right there. Yeah. Arrowhead.
You see this over here?
That's why.
Yeah. But it's doing it more when I connect, so it's whatever. Now we can also have the spring stretched or compressed to a certain point. So think about this. Say that the spring is in equilibrium. We're talking about your car. Right now at a parking lot, your car is the springs right is in the equilibrium position. And then you sit into the car. So that would be this first problem. Your added weight into the car will just bring it slightly down, right? And now, when you the car is slightly down, and then you drive over a branch or something on the road, the wheel will go up, right? And the shock absorber will compensate for that, but the spring still goes up. So you can actually have the spring compressed and then compress it even more. Or you can have it already stretched and stretch it even more. It's just the game of limits. That's all it is, right? So the inside over here has to remain the same at all times because you are not swapping out the spring. This number here says this is the type of the spring that you are now considering. The only thing is over here you say, all right, so the spring is now stretched 10 centimeters, and then we are going to stretch an additional 5 centimeters. So the integral becomes that. The rest of the integral is the same thing. So it's already stretched, and then you stretch it 5 more. So that's all it is. I mean 5 more centimeters, which is 0.05 in meters. Another thing you have to be careful is how the units work out. So that's the story of springs.
So it would always be like the same 100x for like the entire equation.
What?
It would always be the same 100x.
No, because as soon as I tell you that it's going to take this much force to stretch it for that much, you use that to figure out what is the number. What's always there is that it's x dx, right? And it's
like the one that we got earlier said 10 newtons can stretch a spring 0.1 meter.
That's what created 100. Yep.
Yeah.
If I change numbers 10 and 0.1, you're not going to have 100.
Okay.
So this is the equation that you are working with right here, and whatever you calculate goes in for k. Fair?
Yep.
Let's lift some heavy stuff. So this marker is 16 grams in mass, and when I lift it from the desk, I lift the entire marker, so I need to beat those 16 grams. How much force do I need? Well, the force is going to be mass times the acceleration. Acceleration that I have to beat is gravity. So it's going to be 16 grams times 9.8 meters per second squared, meters per second squared. So you can work out the units and see what force I need. And you don't use more force than that. That's it. That's the force that you use. And then force times the distance of how far, right, gives you the work. You can also calculate the potential energy of the object with mgh, which is at the height. So the higher I bring the marker, the more potential energy it has because it's higher. So potential energy is equal to mgh. M is how heavy is the object you are lifting in terms of mass. Gravity is always 9.8 in metric or 32.2 in imperial units. And then you have the height, which is in meters or feet, depending on how far you go. Now, we are neglecting air resistance. You don't. And we are neglecting air resistance, the drag, and everything else because it is, for such a small object, negligible. Now, observe that mass for this object is constant. It's always 16 grams. Gravity is constant, I'd say, because it doesn't change really when you have this. But the height changes. So you see that the bigger the age, the whole number becomes bigger. So higher it is, more potential energy it has. Lower it is, less potential energy it has. If it's resting on the object, you call that height 0 because it's not above the object, it's resting, which means at that point age is equal to 0, so no potential energy in that case. Now if I am to move the desk, right, then the distance between the floor and the marker becomes the distance, and the marker will have potential energy, which, because it wants to fall now, will convert into kinetic energy, which we are not covering here, but kinetic energy 1/2 mv squared is again dependent on velocity and dependent on the mass, and it's a single conversion. So this object has to have energy present. So it's either potential or it's kinetic, and then they swap in between. So the sum of all energies is equal to 0. Now you have a lot of interesting physics problems that you can work out there. What we are interested here is in lifting objects. So as I said, we can use very basic physics to figure out this, because once I lift it, the whole thing is off the ground and we're done. But imagine me lifting a chain.
Like a boat chain?
Any chain, right? You have a chain that it's coiled on the ground, and I pick up the part and start lifting. What can you tell me about that? Yes.
We only need to use enough force for the chain that's above the
Yep. But what's happening with that force?
it's increasing.
It's increasing. Why?
Because as you keep going up, more chains.
Beautiful. So I cannot use uniform force. See, this is always 16 grams. So whatever force I need to master to lift this, it's always 16. But the chain is not. If I only have to, if I'm holding the chain, let's say I have those 5 of those links in my hand, right? That might be equivalent to this, say. But then as I lift, right, I add another 30, another 100 links. All of those have mass. So the more I lift the chain, the more links I add, the heavier it becomes. Now that's the job for integral. And that's where integrals come into place. So now what's changing? The mass is changing. The height is changing. Gravity stays constant, right? So those problems now, we have to figure out how to deal with that. So if I'm lifting something on the vertical, right, I want to have a reference point somewhere and then constantly measure how high I bring. So this height is going to be the dy, c to d dy takes care of that. Then I also have to have the gravity present, and I also have to have the mass, which is what I'm lifting, also has to be present. And we have all sorts of interesting problems, so it's not just lifting the chain or something like that. It's also pumping the liquids in and out of the tank, and maybe you want to empty the pool or something. So we can work with any kind of geometry to figure out. You don't think about that, but when you put the straw inside your drink, right, you have to suck the liquid out through the straw. So there is a force in that part. So for lifting the chain, we have this height over here, which will be taken care of by dy. So to lift the chain, let me just see one thing. All right, so how much work is required to lift the chain? It's clearly going to be c to d, right? Because that's the, and it's going to be dy integral. Now we are going to have, so what I have so far set up there is h. Now we are going to have that vertical component changing, because if this is your 0 level and this is your y level, right, that's changing in time. So what else do I need? What happened?
H minus y.
H minus y. What do you mean h minus y?
Like when you actually set up the equation for your height is changing. That's
Yes.
Is that h minus, like whatever your height is for the
Okay.
given scenario minus y, the change in height.
Yes, the change in
Set
height.
it up?
Yep. And then we need the gravity, right? We can put g in front of the integral actually, because that doesn't impact anything. And we also have a change in mass, right? So what are we going to do for that? Remember the density function, integral of density function? That depends on the, right? Yep.
That F or
Well, it's that density function. Maybe it's a rope, maybe it's a chain, the metal, right? Depending on which one it is.
no, I meant the lettering for it.
Rho,
Bro,
rho, density function.
I don't understand. It's okay.
Density for metal and density for the rope and density for string, different, right? It's different.
Yep.
So the integral of the density is the mass.
So would this be like D then, like NC?
Well, we use rho, but
Okay.
if you want to use D, you can use D.
I think professors a real Y or X.
Y. Thank you. All right. Now let's take a look at. Oh, we are running out of time. So let's take a look at the lifting problems for liquids, because that's. All right. So I'm going to write this out first. So this is the equation. And we have the density, gravity, cross-sectional area, and the distance, vertical distance. Let's do the simplest example first, and then a little bit spicier, and we're done. Say you put cylindrical tank underground, and you store in it water, gasoline, whatever you're storing. On the bottom of the tank, you are going to have the drain, which is going to have a pipe that it's taking the whatever liquid you have inside outside of that tank and above the ground. So if you don't have anything installed, right, the level of the liquid inside the tank will be the level of the liquid that you get inside the tube, right? So you have to have some kind of a machine to push out. Now, you have the height of the tank. So let's say 0 to 10 meters. That's a tank that is 5 times taller than me. So how about we have it as, it doesn't matter, 10 meters, fine. 10 meters tank. And the radius of this is, let's say, 2 meters. The radius of the tank is 2 meters. And then what I have is the height of where the liquid comes out, and let's say that's at 15 meters from the bottom, obviously, because you have the bottom of the tank is going to be the reference point for all vertical measurements. So how much work needs to be done to pump out the water? Now, let's say that the level of the water here is at 7 meters.
Hey, Professor,
Yes.
you mean to pump the water out of the tank, or pump all the water completely out of like the exit pipe?
which is the same thing. Yep. So now, in order for me to do this, this is now application, has nothing to do with our calculations. This is why you are doing this. So you're an engineer who's charged with figuring out what kind of pump you need to push this out. Now, clearly, the pumps that are overkill, they're really expensive, right? So you want to get the right one for the job. You have to compute how much work needs to be done to pump all of this water out, because the amount of work gets converted into the horsepower. Now, if you own a house and you know anything about houses, and you might have the sub pump, it's rated a quarter of the horsepower, or a third of the horsepower, or half of the horsepower, right? If you have a huge basement. So all of that gets converted eventually. So your job is to figure out the work needed. Now we have the equation above, and all we need to do is to plug these things into it and get the water out. So, or whatever liquid. So we start by figuring out the work is going to be. Now, what are you pumping? In this particular case, I want to pump all of the liquid out, and I have 7 meters worth of water. So that's 0 to 7. That's the limits will give me how much. Now, this might be full, and they will ask you to pump out half. What are your limits?
0 to 5.
0 to 5, you're pumping out the bottom, right? Okay.
Well, also, could it be like a negative number to 0, also depending on where your origin is?
You don't want to put your origin on top of the tank.
No, I understand.
Okay, good.
I remember looking at problems where like the one with the sideways cylindrical gas tank would have the origin.
It complicates matters.
Oh yeah.
It complicates matters. So we'll start here. So 0 to 7 meters, right, is the height, and then we have our gravity, right, G, and then you have the rho. Rho is important, the density, because that's what type of the liquid you have, water or a gas or whatever. And then you have the cross-sectional area. Now, cross-sectional area is the shape. This is where geometry now comes in. And if you take a look at this, geometry is the circle, right? So it's r squared pi, which is in this case 4 pi. And I will put circle r squared pi. And then we also have the distance that it needs to cover. Now this is where 15 comes in a place, so it's a 15 minus y. Why is it 15 minus y? Because this is your y distance. Observe that that's filled with water already, right? That y. So you only need to beat the portion that it's not filled in. Does this make sense? So, and then dy. So over here you have, because the level, because how all this goes, this is already filled up to 7 meters. So it only needs to be pumped 8 meters up.
What happens if it's further than, like basically if it's a little bit higher than D1 the tank?
What happened?
What happens if Y value is like a little bit bigger than the
Which you can, because our Archimedes principle, when you have the two tubes that are connected, they all have the same level of water. You can push the pressure on one to push the other one out, but that's interfering with it. If you have two vessels that are connected, you put the water in one, the water in the other one will rise, right, and that's it. Otherwise, you have one ocean to be up to here and one ocean to be here.
That's why we can define physics a lot. And like basically just make the water like go up in the air.
Won't happen. So now, why is this variable driven? it's variable driven because as soon as some water is out, this level is less, then this level is less over here, so then it has more to cover. So this component here will be, it has to be variable driven because the height is constantly changing as you are pumping the water out. So now you can compute this because you kick the constants out, 4 pi g rho, that's all constant, and you integrate 15 minus y dy from 0 to 7, and you get your work required. That's 15y minus y squared over 2 from 0 to 7, and that's 4 pi rho g 15 15 times 7, so what do we have? 15 times 4 is 60, so 105, yeah. Minus, this is 49 over 2. And that's it. That's the answer. Now, since we ran out of time, so on Monday we are going to take a look at 1 or 2 more examples of this for different geometries. We can take a look at the cone. We can take a look at sideways barrels or so on. I believe they have some of the really scary problems that you can challenge yourself with. Let's see.
Yeah, through there.
Oh, the pool, 32. Yeah. That's a real, if you want really to scratch your head for some time, try the pool problem. It's really interesting.